In this lecture, we will study second order filters, and the content of this lecture are going to be like this. First, we will see the generalized second order filter transfer function, and then like the first order filter transfer function, we will take the various cases of second order transfer function, and this time we will see that it will be not only able to represent low pass and high pass, it will also implement band pass and few other types of filtering behavior. And today we will see only the passive implementation of the transfer function. Since there are various possible cases of this second order transfer function, so it will not be possible to consider both passive and active in single class. So in the next class, we will talk about the active implementation. And here we are going to include inductors also in the passive implementation of the second order transfer function, because we in the beginning want to keep the circuit simple. But in the next class, we will see that the inductors can be emulated. That means there will be a circuit not containing inductor, but behaving like an inductor. So we will see those circuits, and once we have that circuit can be used to replace the inductor that occurs in the circuit that we are going to discuss today. So most general second order transfer function possible is given by this expression. Since this is second order, so denominator is second order, and as the definition says that the numerator should be of order less than or maximum equal to that of the denominator. So this is also of second order. So both the numerator and denominator are second order in the general form, but we will see that when we start considering various special cases, those special cases will correspond to special values of these alpha, beta, gamma. That means some of them will be 0, and in that case we will see that numerator can be of 0 order, first order, or second order. So all these possibilities are there for the numerator, but denominator will always continue to be of second order. And we have used different symbols for the coefficients of these two polynomials. In the denominator, we have used omega n and q. We will talk about them shortly. They have a strong physical significance related with the circuit components. So this most general transfer function is second order both for numerator and denominator. So that is why this is called bi-quadratic transfer function. Like last class, transfer function was called as bilinear. So we will see that based on the values of coefficients in the numerator, that means alpha, beta, gamma, it can not only represent low pass, high pass, which we have already implemented using first order, but it will also be able to represent band pass, band stop, and we will see one more filter at the end of this lecture that is called Allpass filter. So as I pointed out, denominator coefficients have been given special symbol omega n and q, and they have some physical significance. So omega n is called natural frequency and q is called quality factor. So we will spend some time trying to appreciate importance of these two parameters, omega n and q, and then proceed ahead with the second order filter transfer function. So since it was pointed out that RLC will be used for implementing the second order transfer function, So let us take a simple RLC circuit, actually only LC circuit. This R is loss of inductor and capacitor, because we know that in real life these inductors and capacitor, they will be lossy. That means when current flows to them, heat will be generated and there will be loss of energy. So that we have separated out in form of RS. And suppose what we do is we start with charged capacitor, that we start it to give some voltage or certain charge to the capacitor and set up this circuit. That means connect inductor and then this resistor. So what will happen to the current? Of course, the current will start flowing, and current will have this sinusoidal behavior, right? So in the beginning, it will be large, but there is a resistor present here. So what will happen is that this energy which was stored in the capacitor, it will start getting converted into heat because of this resistor. So there will be, of course, the decay of the amplitude of the current. And this decay will be actually given by this term, where e raised power minus omega n divided by 2q into t. And ultimately, there will be no energy left in this circuit or in the capacitor or equivalently in the inductor also. So here, uh, this omega n is a frequency where this oscillation occurs. That means this period t will be related with the omega n and given by this expression omega n is equal to 1 by square root LC. Now, ideally, what we would like is that there should be no decay of the energy in the system. That means this R should be as less as possible. So if R is as less as possible, then this decay of the amplitude of the this will be less. So it will be more like this, or ideally it will be flat. So how good this system is at preserving the energy, that is can be conveyed by value of R, or alternatively by another parameter that is called Q, quality factor. So here you can see that the energy dissipated per cycle is in the denominator. So when R goes down, there's this decay in the energy, this will also go down, right? So that means that Q will go up. So this parameter will be able to convey how good this system is at preserving the energy. And that is why this is given name called quality. And so this is called quality factor. This conveys goodness of this LNC system. And since R is basically the loss for this inductor or capacitor, so this also tells, Q also tells how good, how ideal this L and C are. So when this formula is used, say for example in this circuit, focusing on L, because we know that when this oscillation starts occur, the entire energy will be at one moment stored in capacitor and at certain next moment in the inductor. So this can be calculated either in terms of inductor or capacitor. So when you do this calculation for inductor, it will turn out to be Q is omega L by Rs. So here you can see that when R goes down, Q will go up. So this parameter has a strong influence on the behavior of the second order transfer function that we just now saw. Now we are going to consider various spatial cases. So we saw that numerator actually has three parameters, alpha, beta, and gamma. So there are actually various possible configuration, that means various possible spatial cases of this second order transfer function. But we are going to consider only some of them, simpler one, and which leads to well-known filtering response. So for example, first we will start with the cases where one out of the numerator coefficient is non-zero. That means at any given moment, two coefficients will be equal to 0. So the simplest transfer function that we can construct is when we take alpha and beta is equal to 0, so that there is no frequency dependent term in the numerator, and numerator is only a constant term gamma. So this is constant independent of frequency. And second possibility is when we have beta and gamma is equal to 0, so that the numerator is alpha s square. So why we have taken suddenly from a constant case to case when numerator has second order term, because we initially want to study low pass and high pass kind of response. That is why we have taken this particular combination of coefficient for the case 2. These two transfer functions or filtering response we have already studied in the last class. And the third, which is going to give rise to a new response, which was not earlier studied, is when alpha and gamma are taken 0, so that we have a first order polynomial in the numerator. So as I pointed out, there are various possible combinations of 0 values of this alpha, beta, gamma, and we will consider some of them, and a few other cases are also possible. For example, one can take one of the three coefficients 0 at a time. In that way, there will be three possible cases. So we will consider one of the case in this class. So now we are going to consider each of the cases in more detail. We will consider the specific transfer function, try to find out the approximate Bode plot, and actually we will study the exact response also. So first case is when we take alpha is equal to beta is equal to 0. That means only gamma is non-zero. So in this case, we have a second order denominator. In fact, it is always going to be second order and exactly of this form. So in general, there will be two poles, and in general they will be complex given by this expression. And recall that whenever we consider Bode plot, that was considered for real pole. So here you can see that when this term is 0, which implies q is equal to 1 by 2, in that case poles, they are going to be real. So only for q is equal to 0.5 we will get a real, and coinciding real poles. And the pole will be given by this expression, minus omega n by 2q. So we will assume that that scenario exists, and then we will see what will be the Bode plot, and later on we will see the approximate exact response of our transfer function. So when we take for q is equal to 1 by 2, there will be two identical poles and they will be real given by this expression. And in that case, we can see that this is going to be the Bode plot. So recall the response of first order transfer function, low pass response. So that time we had this kind of response. We had pole, one pole, and so this is for the first order filtering response. Let us say this is for the second order filtering response. So what we had earlier was plus 20 dB, or rather minus 20 dB per decay. So this decays slowly. But if you go for the second order, what we get is minus 40 dB per decade slope. That means a transition period. Suppose you want to achieve a decay up to minus 20 dB, then this decay will be achieved here for this much band, but here you will be able to achieve the minus 20 dB of decay over a narrow band. That means this will imply small transition band. So we will be able to move quickly from pass band to stop band very quickly in terms of frequency. And recall that ideally what we want is a big type of response, which is not possible in real life, but that is what is desirable. That means ideally we want this kind of response. So you'll see that there is no function, there is no real life circuit which will give this kind of response, but second order you can see is definitely better than the first order. Now we would like to know that what will be the exact response of the transfer function that we have considered. So here I have taken three possible values of Q. Q in fact can have any value starting from very low to very high. And when you do the exact plot of the transfer function, then this is what you will get. So here we see that when we have a Q smaller value, then there is a smooth transition from pass band to stop band. But when Q is large, then we start getting peak here. And it turns out that whatever Bode plot we plotted, that actually corresponds to this Q is equal to 0.5. So the Bode plot is actually approximation of this Q is equal to 0.5 case. Right. So here certainly whenever we want a low pass type of response, then we don't want this kind of peaking to take place. But this is the property of second order transfer function. Now we would like to know that what is the maximum value of this transfer function, and at what omega this occurs. So of course we will have to differentiate the transfer function magnitude with omega and set it equal to 0 to find out the omega where the peak occurs. Right. So when we set up this equation and solve for omega for which peak occurs, then this is the frequency for which H max is achieved. And this frequency is, you can see, slightly different than the natural frequency. And it is given by this expression. And the peak value will be given by this expression here. Gamma q divided by omega n square root of 1 minus 1 by 4 q square. So now we can see a plot of the second order transfer case function for the case 1, and see where all these values correspond. So this is where omega n will be located, and peak will occur at this frequency, which is slightly away from this natural frequency and given by this expression. So here what happens is that the peaking, that means this curve will start rising above this value for q greater than 1 by square root 2. So whenever q is greater than this, we will start seeing this peaking. And whenever q is less than 1 by square root 2, that means less than 0.7071, there will be no peaking and it will smoothly decay. And for q is equal to 0.5, the Bode plot gives the best approximation to this transfer function. Right? And when we go for this region, then here what we will see is decay of minus 40 dB per decade. But in this region, around this omega max or omega n, there will be huge deviation from the Bode plot. And gain at DC is given by this expression, gamma divided by omega n square. Now here I have plotted the transfer function for various values of q, and here you can see that the critical value uh, after which the peaking start is also given here, which is 1 by square root 2, and three usual values, they are already there. So this value is for Bode plot, q is equal to 0.5, and this one is boundary line between peaking and no peaking, and then 0.1 and 10 are two usual values. So here we have magnitude of the transfer function, and here we have omega in log version, and the first curve, this one is for q is equal to 0.1, this is for q is equal to 0.5, for which we get the Bode plot, and this green color is q is equal to 1 by square root 2, and that is the boundary line after which this peaking will start, and this one is for q is equal to 10. So when you increase the q, this peak will grow, this will become larger and larger like this. So q, say for example 50, right? So this tends to become more like an oscillator. That means energy will be stored in the system and it will decay with a very slow rate, and that is what oscillator is intended to do. It is uh, required to store energy forever with ideally no decay in the amplitude of the periodic signal, which will be in this case sinusoidal. Now we consider the case 2, where we have taken beta is equal to gamma is equal to 0, so that numerator is second order. In fact, only second order term is there, and denominator remains as usual. So here you can see that since numerator is s square, so there are two zeros at the DC, right? So that means at the low frequency, we will have a Bode plot which will increase, and in this case at the rate of plus 40 dB per decade. And there are two poles given by denominator, and in general we have seen that they are going to be complex. Right. So we have a 2 0 at low frequency. So what it does is that when you decrease the frequency, they will be attenuated at a rate of minus 40 dB per decade. So the lower frequency, they will be greatly attenuated, and in this case, for real poles, the transfer function will become, say, alpha s square plus s plus p whole square. So two real and coincident poles So in this case, we can see that what will be the Bode plot. In the beginning, the zeros, they will dominate, and there are two zeros. So what we are going to get here is a slope of plus 40 dB per decade, right? And then after this pole P, we again have two poles. So this slope will get neutralized, and this is going to be the response. So this is the advantage of second order, that we are going to get plus 40 dB rise, or when we move from high to low frequency, there will be attenuation at the rate of minus 40 dB per decade. But for the first order uh, response, we saw that it will rise with a rate of plus 20 dB. So we see that the order has a huge advantage uh, in terms of attenuating the signal in the stop band. So here also the transition band, suppose we want attenuation of minus 40, minus 20 dB, then the transition band in this case is going to be narrow compared with here, where transition band will be typically wider. So this is the advantage, but we will see that the circuit complexity increases when you increase the order, and typically size also increases. So we will be trading, we will be getting advantage in terms of transition band at the cost of circuit complexity and size. So when the circuit complexity increases, designing also becomes complicated. Now here we have exact plot of the second order transfer function for case 2, and here we have the same usual values. This is for q is equal to 0.1, and this is for q is equal to 0.45, which corresponds to Bode plot approximation, and this is for q is equal to 10. So here also we would like to know what is this peak value, and what is the frequency for which this peak occurs. So this can also be found out by differentiating the transfer function with omega and setting it equal to 0. So when we do this exercise, the frequency for which h becomes maximum is given by this expression. It is omega n divided by this factor. Keep in mind that earlier this factor was in numerator along with omega n, but now it is in denominator, right? So this frequency is going to be higher compared with the omega n, because this factor will be typically less than 1. And the maximum value is given by this factor where we have alpha q divided by 1 minus 1 by 4q square. So we can see all these values here in the plot. So this is the maximum value possible, and this occurs for omega max, which is here, and greater than. So this omega max is greater than omega n, and it will be slightly away from omega n. This gap is typically very small, and it reduces very quickly as the value of q is changed. So here we again have peaking occurs when q is greater than 0.7, and when q is less than 0.7, there is no peaking, and in between we have or in fact smaller than this case corresponds to the Bode plot case. And value at infinity is of course given by alpha. Now we have case 3, and this is a new case in terms of the nature of the transfer function that will be revealed by this transfer function. So here we have taken alpha is equal to gamma is equal to 0, and numerator in this case is of first order. So here we see that we have 1 0 at DC. That means in the beginning transfer function will have this kind of behavior. That means it will suppress low omega components, and we have two poles, and again they will be complex in general, but when we take the special case they will become real and we will have two coincident poles. So what happens here is that one pole will neutralize this behavior, and then it will start decreasing it with minus 20 dB per decade. So what we observe it, 0 at DC and at infinity attenuates low frequency and high frequencies at a rate of minus 20 dB per decade. So only frequencies somewhere in the middle, they will not get attenuated. Rest all on the left side of that frequency and on the right hand side, both will get attenuated. So we have taken the transfer function, and it is like this. So if we have a real pole, coincident pole, scenario will become like this. So here you can see that the transfer function will have a slope of plus 20 dB per decade in the beginning, and once you reach to the pole, first pole will make it flat, and then second pole will give rise to decay with minus 20 dB per decade. So this is the kind of response we are going to get out of this second order transfer function, provided the poles turns out to be real. So here you can see that only frequencies which are in the neighborhood of this pole, they will not get attenuated. They will be typically of the same value, certain constant value, but rest all other frequencies, what we will have here is stop band. Similarly, on the other side also we will have stop band. That means all the frequencies beyond this will get attenuated, all the frequencies in this region. Only this will be the pass band. Now let us see the actual plot of the transfer function for various q's. So here we have q is equal to 0.1, and here we have q is equal to 0.5, and this is q is equal to 10, right? So here you can see that we have a slope of 20 dB per decade. Similarly, here we have minus 20 dB per decade slope. So only the frequencies in this region, they actually either they don't get attenuated, or in fact some of the cases we can say that they get amplified also, sort of. So what we do is for this case we defined a bandwidth. That means we have to recommend what is the lower frequency and what is the upper frequency between which we should use this circuit. So for that, what is done is that we take the peak value, this peak value H max, and then we say that those frequencies where this H max gets reduced to 1 by square root 2. So we draw a line at 1 by square root 2, and the frequencies corresponding to that 1 by square root 2, they are called lower and upper or higher frequency, and frequencies between these two limits, they are considered to be allowed to pass on the output side, and we say that this is our pass band, and we say stop band, or actually in the beginning there will be transition band. So on both left and right, we have stop bands. And this 1 by square root 2, if you calculate in dB, this value will turn out to be 3 dB. And since it is 3 dB below the maximum, so this is also called minus 3 dB. And that is why this bandwidth that is omega h minus omega L. This is called minus 3 dB bandwidth. Now one can find out expression for this minus 3 dB bandwidth. So here also one has to differentiate the transfer function with omega and set it equal to 0 to find out that omega for which peak occurs, this omega max. And in this case, omega max turns out to be equal to omega n. And the maximum value that will occur is given by beta q divided by omega n. And since we know the maximum value, we know the transfer function, so one can calculate the minus 3 dB frequencies omega L and omega H by setting up equation. So as per definition, minus 3 dB frequency is frequency where the transfer function becomes 1 by square root 2. That means 0.7 times of the maximum value. So here we have a transfer function, and here we have a maximum value. So this omega will give rise to omega L and omega H. So when we set up this equation and solve, this is what we get. So here omega L is omega 2 and omega H is omega 1. And they are given by this expression. So they depend upon Q and omega N. Both. So now here is graphical representation of all the parameters related with the bandpass filtering response. And here we get one more relation that those omega L and omega H, they will be related with omega N, which is also sometimes called as omega naught at the center frequency. Of the bandpass filter. So here we have maximum value H max, here we have H max by square root 2, and here we have omega L, and this is omega H. So bandwidth is omega N divided by Q. So here one thing to note is that when we increase Q, bandwidth decreases. And this we can see from the plot also. Here you can see that when Q is 0.1, we have a wide band. When Q is 0.5, we have narrow band. And when Q becomes 10, we will have still narrow band. Because here you can see that if I plot minus 3 dB with respect to this, so minus 3 dB will be like this. So you can see that bandwidth is only this much. But here for this case, if I do the minus 3 dB plot, so this was the band I got. But for this case, if I do the minus 3 dB, then this is minus 3 dB. So here you can see that bandwidth is increasing. So Q and bandwidth, they are inversely related. And this is a very strong relation, and this will be present in all the filters. And from here, sometimes we experimentally try to determine Q for a given circuit as omega n divided by delta omega, where delta omega is this bandwidth, omega 2 minus omega 1. So you set up circuit, and from the spectrum analyzer, you can measure this or frequency. You can do the frequency plot, and You can measure this delta omega, we can find out the center frequency, and from that you can determine Q of the circuit. Now we will see the various implementation of all these three circuits. So the general architecture, fortunately for passive version, remains similar to what we studied for the first order circuit. That means we take two impedances, ZP and ZS, and transfer function given by ZP divided by ZS plus ZP in general will be able to represent all the possible cases of the second order filter transfer function. And based on the nature of this ZP and ZS with frequency, this will represent low pass, high pass, or band pass response, the kind of thing that we already studied for the first order filter. So for example, when ZP goes down with frequency, then this will represent low pass kind of filter. So in the last class, it was pointed out that in the indicated circuit, we avoid inductor because that make the circuit size very large. But here we are considering inductor so that we wanted to keep this transfer function very simple. And in the next lecture, we will replace this inductor by a circuit consisting only of RC and op amps. So that can be used to implement the inductor and ultimately keep the circuit size small. Right. So here, suppose we take a series inductor and capacitor and resistor in parallel at the output. Then the transfer function that we will get is given by this expression. So here you can see that gamma is 1 by L1 C1, and denominator is second order. So this is the second order kind of filtering transfer function. And here we see that this ZP should go down as frequency goes up, and that will happen because of this C, because we know that the impedance offered by this is omega C. So this part will start dominating as the frequency goes up, and more current will flow through this, so this voltage will go down. Right. So we have this transfer function. When we compare this with the standard one, we can find out Q and omega n for this circuit. And Q is R divided by square root of C1 L1, and omega n is usual 1 by square root of L1 C1. So here we will get this kind of transfer function plot, and this is low pass or low pass filter. Now if we interchange the location of L and C so that this starts offering low impedance when frequency goes down, in that case what we will see is attenuation of low frequency components, and for a high frequency component this will act like an open circuit. So there will be finite value of output larger than the typically lower value cases. So in that case we will have a high pass type of response, and the transfer function here you can see is given by this expression where alpha is given by L1 C1 R1. And denominator, you can see that it is same as the previous case. So in this case also omega n will be 1 by square root of L1 C1, and Q will be given by R into C1 by L1, the expression that we got for the previous case here. Now for the general case, what we want is we want certain intermediate frequency not to be attenuated. That means for intermediate frequency, the path in this direction from towards the ground should be a very high impedance or ideally open circuit, right? So that can be achieved by putting two L and C in parallel, right? So here you can see that the admittance of this path is going to be 0 at omega is equal to 1 by square root of L1 C1. So that means there will be no current flowing in this direction. That means no attenuation, and this output will be high. So this is how qualitatively you can analyze the behavior of circuit. But when frequency goes down, when omega is low, this path, this will start offering low impedance path, and most of the frequency they will get attenuated. That means they will develop very low voltage here at the output. However, when we have a high frequency, when omega is high, in that case the capacitor will offer a very low impedance path, and again there will be low voltage here at the output. So we see that we get low response for small frequencies because of inductor, and again low response at the high frequency because of capacitor. And only at the center what we get is non-zero response. So this is going to be the pass band. So these three we had already studied, pointed out for various cases. Now we are going to consider a fourth case. And in this fourth case, what we have done, we have taken only one of the coefficients to be 0. For example, beta is equal to 0. So now we have a second order term and a 0th order term. So on the whole, this numerator is still second order. And in this case, if you do the plot, what will happen is that there will be one frequency, omega n, which will be completely suppressed, eliminated, and it will not be allowed to pass, reach on the output side. Rest all the frequencies will be typically allowed. So here what we have is, we have here pass band on this side, similarly on this side also. So here stop band is in between. This is stop band. Actually, this bandwidth can be very small, and it will sort of suppress or stop only one frequency, and that is why this is called notch filter. But in general, this kind of response leads to a filter which is called band stop filter. So notch filter is special case of band stop filter, and the transfer function will be given by this. So here bandwidth is given by omega n divided by q, and omega 1 and omega 2, they will be related as usual for the band pass case, and the bandwidth is this omega n by q, and this is actually complementary of the band pass filter. So this is band pass filter. So this is inverse behavior of band pass filter. So what we want now is, we do not want one frequency to reach on the output side. So what we want is no current should flow through this, only at one frequency. So that can be achieved by interchanging the location of parallel LC with R in the band pass circuit. So here at omega is equal to 1 by square root L1 C1. So this path will be open, admittance will be 0. That means impedance is going to be infinite at this frequency. So since this at this frequency, equivalent circuit will get reduced to this form. So clearly you can see that V output is going to be 0 because this path is open at this frequency. And for this circuit, if you find out the transfer function, it will be given by this expression. So here you can see that we have S square term, we have gamma, so this one is alpha, this is gamma, and the denominator remains as usual of the same form. That means here again Q will be given by this expression and omega n by the expression that we have been encountering for all the previous cases. So these four filtering response are very common. They are very frequently used in real life. Now we are going to consider the fifth case. That is a very special case, and that case is called all-pass filter. So in the beginning, it will be very surprising to see that why we need this kind of filter. So here is the magnitude of the transfer function, actual transfer function with respect to frequency. And here you can see that numerator is the most general second order, but there is a strong relation between numerator and denominator. You can see that both are of exactly same form except this sign has been changed. So here in the denominator we have plus, in the numerator we have minus. So now here you can see that when you take the magnitude, and it is this S term which gives rise to j omega, and this is real, omega m square is real, S square is also real. So you can see that magnitude of numerator and denominator, they are exactly same, and the magnitude will turn out to be equal to alpha. So for every frequency, the transfer function, the output will always be constant. So here it might turn out, it will in fact appear as very surprising why we need this kind of circuit which gives the output exactly same as the input. Right. So here what we have is, this implies mu is going to be equal to alpha Vi. So keep in mind that this output, it has magnitude and phase. That means this also has both magnitude and phase. So up till now, that means up to case 4, we focused only on the magnitude of the transfer function. We never talked about the phase. That means we wanted signal, output signal to be of certain relation with the input in terms of magnitude. Phase relation was not important. But there are certain applications where what we want is the magnitude should not get affected when signal reaches on the output side, but its phase should get affected in certain way. And it is for those scenarios where we need this kind of all pass filter. Because here if you see the phase response, so here what we have is phase of the transfer function. So here we see that the phase changes with the frequency. It no longer remains flat. Right. So where we will require this kind of a filter. So what happens is that there are certain circuits where if you see the output, then this output will gain certain phase, right? So say for example, output could be sine omega t plus phi, and phi itself will be frequency dependent. This phi, the output signal phase, will change with the frequency of this input signal. So when this frequency changes, the phase changes, and then what you will see here is the shape of the output will no longer remain same as of this one, even if the amplitude remains same, because we know that sum of two sinusoids or multiple sinusoids will be decided not only by the amplitude that you see here, but also by the phase. So there are certain media, they are called dispersive media, where what they do is they introduce different phase based upon the frequency of the incoming signal. So those signals are then again required to pass through another system which will neutralize the phase gain that various frequencies have obtained when passing through this dispersive medium. So then we will put another system at the output of this. So here we will put all pass filter so that whatever phase gain they have obtained here, that phase can be neutralized by making them pass through a all pass filter with certain phase characteristics. So these circuits, they are also useful all pass kind of circuit in the real life. And one of the ways of say implementing this all pass circuit is here. So if you try to find out the transfer function for this case, V output versus this V input, this is what we get. So here you can see that only the sign of the first order term is different, everything else is same. So these are the five types of filtering response that we can get, and these are the references for this lecture.